Hello. Before we try to understand hyperoxaluria per se, first we should have some confidence in understanding the structures of the compounds involved in the whole metabolic pathway. We have oxalic acid, we have glycolic acid, we have glyoxylic acid. This will be the site of confusion for every student when he wants to understand the link between that of glycine and all these three compounds. What is common to these compounds? All these compounds are carboxylic acids, while glycine is an amino acid. You have NH2, CH2, COOH. Now, if at all you look at these two carbons are the common things between glycine on one side and oxalic acid, glycolic acid, and glyoxylic acid on the other side. Now, all these three are just acids, while glycine is an amino acid. So, if you want to make the glycine comes towards any of these three compounds, it has to lose amino group. If at all these compounds have to go become glycine, then they have to gain an amino group. So, you will understand transamination is an important concept in this particular part. Transamination means if I have glycine or I have serine or any kind of amino acid like proline, you are supposed to attack the amino group. When the amino group is lost, the remaining acids is what we are discussing. Now, our goal, the hero of this whole chapter, is oxalic acid. We are looking at how oxalic acid concentration can increase in the blood because of some defects. Now, hyperoxaluria can be of three types. You have hyperoxaluria of three types. Type 1, 2, and 3. At that point of time, you have to understand 1 and 2 are defects where a transaminase enzyme or another enzyme will both be involved in deficiency. While in case of 3, mutation happens in such a way, this enzyme will be hyperactive. There are three types of primary hyperoxaluria: type 1, type 2, and type 3. We'll discuss about these three sooner, but before that, type 1 and 2 will have mutations in the enzymes where the activity of these enzymes will be elevated, decreased. Now, in case of type 3, the mutation has happened in such a way that relevant enzyme activity is increased. Now, look at this part here. We will be concerned about peroxisomes and mitochondria together. Now, when you learn about packaging disorder, that is, the particular enzyme is supposed to be in the peroxisome, but it is not sent to the peroxisome. This enzyme is a protein. This protein is synthesized by the ribosomes, and those ribosomes will actually take the help of Golgi apparatus to push the proteins into this area. Now, if at all there is a mistake in the trafficking of this enzyme, that is the transferase, into the peroxisome, then the activity of the enzyme in the peroxisome is deficient. So that you will also remember the same enzyme can be effectively present in the mitochondrion, but its activity is not important and relevant. Not relevant and useful in case of mitochondria. It should have been useful only if it was placed in the peroxisome. So let me repeat, this enzyme should be in the peroxisome for its activity to happen. But because of the mistake in the trafficking, it has gone to the mitochondria where its activity is not relevant and not useful. Now look at this pathway here. Generally, if you look at diet that contains collagen, or you look at vegetables, that is when you try to eat meat, as in case of carnivores, or when you try to go for vegetables, both can be the source of ultimate hero called as oxalic acid. Now, from collagen, you have hydroxyproline. That hydroxyproline will be converted into 4-hydroxy-2-ketoglutarate. Till here, you'll be having a 4-carbon compound. Now, here I'll be having an enzyme which is 4-hydro-2-ketoglutarate aldolase. This enzyme is an aldolase. Now, this aldolase will be able to convert 4-hydroxy-2-ketoglutarate into glyoxylate. Now, this glyoxylate can either become glycine or it can become glycolate. Remember, what you have is mitochondria. This indicates mitochondria. And in the mitochondria, the enzyme Ag2 will be active but not relevant to our health. It is not going to help us. Now this Ag1 or Agt1 should be present in the peroxisome. If it is happening here, it will work. So what was the purpose of telling you about the name of the compounds? Oxalic acid is both carboxylic groups. Glycolic acid is one being a carboxylic group, the other is an alcohol. The glyoxylic acid means one is an acid, the other one is an aldehyde. So you have acid here, alcohol here, and aldehyde here. But what have we understood from chemistry, organic chemistry? Alcohol on oxidation becomes aldehyde. Aldehyde on oxidation becomes acid. Now you can go in the reverse pathway. Acid on reduction becomes aldehyde. Aldehyde on reduction becomes alcohol. Here, if I want to go from glycolic acid to oxalic acid, it is alcohol to acid, which will be oxidation. If I want to go from glycolic acid to glyoxylic acid, it is alcohol to aldehyde, that is also oxidation. But if you want to go from aldehyde to alcohol, that is reduction. Acid to alcohol, that is reduction. That is why we have oxidase enzymes becoming very important. Now this enzyme is glyoxylic acid. Glyoxylic acid reductase, plus it also has hydroxyproline reductase activity. It has 2 reductase activity. Now because of this, it is capable of causing reduction. Now we have glyoxylic acid present in the cytoplasm. Because of this enzyme called as GRHPR, it will be able to convert into glycolate. The moment it becomes glycolate, it will be able to become hydroxypyruvate. From there, I'll be able to generate glycerate. Now, let's not focus on this area. Let's focus on this area. If this enzyme is deficient, glyoxylate content can increase and can lead to oxalate. Again, oxalic acid concentration can increase. Now, if this enzyme is deficient, glyoxylate cannot become glycine and glyoxylate will be accumulating. If that glyoxylate goes back into the cytoplasm, again with the help of the dehydrogenase enzyme, it can become oxalic acid. Now, if you look at this one, I repeat, here, in case of hyperoxaluria type 1, there is a decrease in the activity of AGT1. Now, let me erase all the annotations here. Look at this part. If at all you speak about primary hyperoxaluria 1, then it is AGT1 deficiency, because of which glyoxylate accumulates, and that glyoxylate will have a reversible activity of entering into the cytoplasm where it can become oxalate. Again, oxalate concentration increases. Now, type 2 hyperoxaluria means this enzyme is deficient. It is not able to convert glyoxylate into glycolate. Again, glyoxylate can become oxalic acid. Oxalic acid concentration increases. Now, I told you, in type 3 primary hyperoxaluria, there is a mutation that causes increase in the enzyme activity, and that enzyme will be HKA. Now, this will be able to convert seamlessly the hydroxyketoglutarate into glyoxylate, and that will increase the glyoxylate content to go to oxalic acid. I told you AGT21 will not be very useful in our condition, because of which glycine production may happen or may not happen. But if this enzyme is hyperactive, glyoxylate can increase, very less amount can go to glycine and glycolate, but more amount will go to glyoxylate to become oxalate. So we have 3 reasons why oxalic acid concentration increases. And the problem is there is a defective trafficking. The AGT1, which is supposed to be present at the peroxisome, has not been sent here. Instead, the mitochondrial enzyme is present, but that is not capable of helping us. Now, what are the reasons here? Type 1, type 2, type 3. When you have an aminotransferase, alanine glyoxylate aminotransferase deficiency called as AGT1, this is an aminotransferase. If this is not effective, oxalic acid can increase. And oxalic acid concentration increase in cytoplasm, that will go into the blood. In the blood, it can cause oxalic acidemia. And whenever the oxalic acid concentration in blood is increasing, oxalic acid level in the urine will increase. That is the reason why it is called as hyperoxaluria. Now there is a question. Why is it called as primary and why is it called as secondary? For example, in any kind of condition, when they use the word primary, it means the problem is within. When they say secondary, the problem is outside. An outside problem is the reason for something to happen. Now, if I say primary hyperoxaluria, the oxalic acid concentration is increasing because of the genetic defect in any of the enzymes that are involved in the metabolism of glycine. But when we go for secondary hyperoxaluria, the oxalic acid concentration is increasing not because of the problem in the pathway, it is because of the increase from the sources. What are the most common sources? Look at this part. when you go for any kind of jejunal bypass, partial gastrectomy, bariatric surgery, you are removing most of the part of the intestine. So colon will be intact. Colon will start reabsorbing oxalic acid maximally, and this is the reason for enteric or secondary hyperoxaluria. Also, ethylene glycol is actually an antidote for something you remember from school, yes or no? And that ethylene glycol, if you take it by some people who actually want some kind of high, they take it as alcohol equivalent. If this is taken high, that is also capable of increasing your oxalic acid concentration. And vitamin C excessive increase can actually produce gluconic acid, or it can produce gulonic acid. From there, you will be able to produce more amount of glyoxalic acid. Also remember, increased intake of tomatoes can also lead to increased levels of oxalic acid. And what is the result of oxalic acids going through the urine? When in case of urine, hyperoxaluria means the oxalate is the end product of metabolism. High levels of oxalates are toxic. They start accumulating in the kidney. If it accumulates in the kidney, it can happen in the calyces. But if it happens to be in the ureter, it can cause block in the flow of urine. Now the urine can keep on accumulating. As the fluid increases, the kidney size increases. That will be referred to as hydronephrosis. Water has actually made the nephrons swell. The whole kidney has swollen. Now look at this part here. If it is unaffected person, nothing will be here. But as it goes for chronic kidney disease, the oxalate stones will look like this. And these oxalate stones can actually react with calcium to form calcium oxalate. And because calcium as a mineral is capable of being X-ray opaque, it can be seen on the X-rays. Nephrocalcinosis can be seen. Calcinosis, calcium levels are increasing. Nephro in the kidney. So oxalic acid crystals in the kidney will cause nephrocalcinosis because the oxalic acid can bind with the calcium. If this keeps on happening, oxalic acid can actually stud your whole kidney with a lot of stones, and it can create kidney failure later. Chronic kidney disease stage 4 to 5 can happen. If it is ultimately going on, then you can actually go for dialysis to save your kidney. It is better not to actually allow the oxalic acid levels to be higher. There are certain drugs which can increase the excretion of oxalic acid, but it can also cause decreased synthesis of oxalic acid. Now this is a homework. Find out the name of the drug that is capable of inhibiting this enzyme called as GRHPR. It ends with SAM. Now remember the treatment. Some people can say, if the concentration of oxalic acid should be decreased, then oxalic acid intake should be decreased. No matter oxalic acid being less intaken or more intaken, oxalic acid's primary source is endogenous. So if you don't give it from outside also, your body will be producing more from within. That is the problem in case of primary hyperoxaluria. I hope this helps your understanding. Thank you.